Hi, everyone. So we got a lot of requests to do a course related to the introduction to mathematics for machine learning. So we want to host this series or start a series that is actually looking into this. And this is the first in hopefully many lectures to come on the mathematics of for machine learning. Now, please notice that this is a introductory series of lectures, meaning that you might know a lot of this material, but it is targeted at an audience who's new to machine learning and is actually interested in learning the fundamental mathematical concepts that are used in machine learning. For that, we use this book, or we follow this book, which is a great book from Mark Deisenroth, Aldo Faisal, and Cheng Song Ong. And the topics we will cover in this series of lectures is going to include linear algebra, vector calculus. So linear algebra is needed, when you are doing like these forward passes in neural networks, for example, where you're multiplying matrices by vectors or matrices by other matrices when it comes to attention mechanisms of transformers. Vector calculus is needed, for example, when you're going to do gradients and do backpropagation. We're also going to talk about probability theory. And then last, we're going to kind of apply these things all together to derive some very famous loss functions in machine learning, like things related, for example, like a probabilistic interpretation of an MSE loss or a cross-entropy loss. So what we're going to do is we're going to start with the linear algebra part in this first part of the series, and then we're going to continue through those topics I described. Okay. So to start with linear algebra, we are going to be talking about vectors in Euclidean spaces. So we're not going to talk about the more advanced subjects for now, but we're going to be looking into what Euclidean spaces mean, talk about definitions, some properties, and some examples, and then we're going to map those into some machine learning related material. And then we're going to talk about lengths, inner products, norms, and metrics in these Euclidean spaces. So these are things related to, for example, how you measure distance between points. And then we're going to talk about linear independence in that context as well. Then in terms of matrices, right, we're going to talk about what a matrix is and what are some of the properties of these matrices and give you some examples. Then we're going to talk about traces, inner products, norms, and metrics for matrices. Followed by that, we're going to talk about positive, semi-definite, and symmetric matrices. And then we're going to discuss eigenvalues and Cholesky decompositions. So I hope this series will give you a comprehensive introduction of what is needed for machine learning from a mathematical perspective. So let's get started with Euclidean spaces. So what are Euclidean spaces? So Euclidean spaces are defined as a space, right? So there's a space in any finite number of dimensions n. So we have a space, right? And that space has a set of dimensions n, and these dimensions are finite, so they're not infinite. And the points in that space are designated coordinates, one for each of those n dimensions. So to describe that point in space, you will need n coordinates, and we will say what a coordinate is, right? But for now, imagine a space, and that space has n dimensions, and points are designated by coordinates, right? One for each dimension. And you have the ability to define distances between points by some distance formula. Okay, so a Euclidean space is a space in any finite number of dimensions n, and the points in those dimensions, they have coordinates, one for each of those dimensions. And there's a way you can define distance between points using some distance formula. Now, when you read machine learning papers and you see a notation that looks like this, r to the power n, this is a typical notation we are using to describe, for example, a Euclidean space. So when you really look into this r to the power n, what we are actually saying that we have a space in n dimensions, right, made of real numbers in this example, and each of those points in that n dimension can be described by coordinates, and we can define distance between these points. But what are coordinates? So coordinates, we can define it as follows. So an ordered collection of n numbers. So if we have n numbers and we have an ordered collection of them, identifying the location of the points in the space, so where those points are located in the space, with respect to some reference line, we call those the coordinates. So here's an example, right? So a R1 Euclidean space is a space that looks like this, right? So this is a line, just a line. That's the coordinate axis, right? It's just one-dimensional line. And here you have like points like -1, 0, 1, 2, and so on. And then here you can have a point A, which has like a 0.5 value that can be located on this line. So the coordinate of this A is 0.5, and it can be located on this line. Here's a two-dimensional Euclidean space, where now instead of having one coordinate axis x, we will have two coordinate axes x and y. And why we need two? Because now we are in R2, right? Meaning that we are in a two-dimensional Euclidean space. So we need two axes, two coordinate axes to define a point for us in that space, because we need to localize it across the first dimension and we need to localize it across the second dimension. So here's an x and a y, which are like these two-dimensional Euclidean space or two-dimensional coordinate axes, right? And then you can localize a point in this two-dimensional Euclidean space by giving two numbers. For example, here a is equal, the point A is located at 1.5 across the x-axis, so 1.5 across the x-axis, and 1 across the y-axis. And now here's a R3 Euclidean space. So here we have a Euclidean space in 3 dimensions, and to be able to describe, right, this Euclidean this point in this three-dimensional space, we need 3 coordinate axes because we're in R3. So we would need x dimension, y dimension, and the z dimension. So now any point you can describe in this space is made of 3 variables, 2.5, 2, and 1.5 in this example, but this is the first dimension that will allow you to localize it across the x coordinate axis. This is the second dimension that will allow you to localize it on the y coordinate axis, and this is the third dimension that will allow you to localize it on the z coordinate axis. Okay? So now what we can do is we know at least what a Euclidean space is, right? So that's any space or a space that has a finite number of dimensions. You can describe points by coordinates, right? Where coordinates is an ordered collection of endpoints, and they describe how much you move in one of those different coordinate axes. Now, we can also define a distance formula, right, inside that Euclidean space. So what that means is the distance formula is an algebraic expression, right, that will give us distance between pair of points in terms of their coordinates, right? So remember, if we go back here, if we go back here, you notice that, for example, in R2, right, a point A, it has 2 coordinate axes values that can describe this point A. So, for example, you have 1.5 and 1, right? Okay. Now, what you could do, right, is that now you can define a distance between 2 points, say A and some other point B, right? So imagine I have some other point B somewhere here, let's say, right? And that point B, it will have a X coordinate and a Y coordinate, right? Maybe in my example, it's like 0.9 and 2.1, you know. Now what you could do is you can actually define a distance between these 2 points in that Euclidean space. So how would you define this distance? So if we are talking about R1, the distance is really just the distance between these 2 points A and B is nothing but the absolute value between the difference of the coordinate of A and the coordinate of B. So for example, if I have these 2 points A and B, where A is located at the coordinate 0.5 and B is located at a coordinate 2.5, right? Then I can do the absolute value of A minus B, right? Or B minus A, right? Because the absolute value doesn't change. And then I will get the distance between A and B. So in this example, let's say you get 0.5 minus 2.5, right? So that you get minus 2, an absolute value of minus 2 is 2. So now the distance between these 2 points A and B is actually 2. You can do the same in 2 dimensions. However, in 2 dimensions now, the distance formula between A and B will become the square root of the difference of the first coordinate value squared plus the difference of the second coordinate value squared. So for example, the distance between these 2 points A and B, if A is located at 1.51, right? So remember, we can localize this at 1.5 and 1. So that's the point A, 1.5 across the x-axis or x-coordinate, and 1 across the y-axis or y-coordinate. And B is at 0.5, 1.5. So it has 0.5 for the x-coordinate and 1.5 for the y-coordinate. Now, to define the distance between A and B, right, what we're going to do is we're going to take the difference in the x variables or x coordinates and square them, take the difference between those in the y coordinate and square them, then we're going to add them together, and then we're going to take a square root. So this is what this formula is showing you. You take the x and you take for the first point and the x of the second point, you subtract them and square them. And then you take the y for the first point and the y for the second point, you subtract them and square them. And then you take the square root of the sum of the two. So in terms of our example that we have here, so xa is 1.5 and xb is 0.5, right? So that's the how far I will go in the x coordinate to have A and how far I will go in the in the x coordinate to have the point B. And then I just subtract 1.5 from 0.5, right? And then I would square them. And then I would also subtract the y variables, right? So I will subtract the 1 from 1.5 and also square them. And then you would notice that the distance between these two points, A and B, would actually be square root of 1.25. Now you can do the same, but in any Rn, so not only R2, because this is a two-dimensional Euclidean space, but you can do it in 3, 4, 5, and so on. All you need to do is you need to take the corresponding coordinates from the two vectors, subtract them, square them, then add the subtract and the squared difference of the second coordinate. So for example, if we have a three-dimensional Euclidean space, and remember, in a three-dimensional Euclidean space, we need to be able, right, to have three values in order to define, right, the three-dimensional Euclidean space here, because we need three coordinates to define a point. So that's, for example, point A. It moves 2.5 in the x coordinate. It goes 2 in the y coordinate, right? And then it goes up 1.5 in the z coordinate. And the point B, for example, right, which will go 3 steps in the x coordinate, 1 in the y coordinate, and 2 in the z coordinate. And now you can define the distance the same way we've done in the two-dimensional Euclidean space, but simply now you need to just add the additional dimension or the additional coordinate subtraction squared. So what you really need to do is you will take the x from the x and square it. You will take the y from the y and square it like we've done in the 2D space. But now we have an extra coordinate, so we'll take that from that, 1.5 minus 2, so z from the z and square it, and then square root everything. So for example, here you will see that the distance between a and b is going to be the xa minus the xb, so 2.5 minus 3 squared, the ya minus the yb squared, which is going to be 2 minus 1 squared, the za minus the zb squared, which is going to be 1.5 minus 2 squared. We sum them up, and then we take a square root, and then you will get a square root of 1.5. Right, so now we know, right, how to take distances in the Euclidean spaces, right? All I need to do is I will take, those two coordinates, and then so I will take, the corresponding coordinates between the points. So I'll take the x from the x and square that. I'll take the y from the y and square that, add them together, and take a square root. So as we've done here. So in Euclidean spaces, so in general n-dimensional Euclidean spaces, because we took an example of 1 dimension, we took an example of 2 dimension, we took an example of 3 dimension. But now we can define this in any n-dimensional Euclidean space. So in an n-dimensional Euclidean space, remember our notation r to the power n or rn. Each point, as we agreed, will be designated n variables, right? Or n coordinates, because in n dimensions, right, we will have n coordinate axes. So we said in 1 dimension we had 1 coordinate axis, in 2 dimension we had 2, in 3 we had 3, right? Because we need 2 values to locate a point in 2D. Now in n dimensions we need n coordinates to locate that value in this n dimension. So for example, let's say you have a point A, which has these n dimensions, so x1, x2 up to xn, all right? So this is its location with respect to the first Euclidean or to the first coordinate axis. This is its location with respect to the second coordinate axis, and third location with respect to the third coordinate axis, and then the nth location with respect to the n coordinate axis. So let's say we have this point A, and also let's say we have this point B. So we give a notation here x1 A, x2A, xnA, to say that, okay, this is for the point A, its coordinate on the first coordinate axis, second, third, and nth. And similarly for B, so we give it x1b, x2b, up to xnb, right? And then the idea here, x1b, x2b, and so on, is the location of the point B on the first coordinate axis, the second coordinate axis, and the up to the nth coordinate axis. Now we can define the distance between these 2 points A and B, right, as the square root of the sum of the squares of the corresponding coordinate axis values. So if you look at this equation, right, and you just write it out, you will see that this will be x1a minus x1b squared plus x2a minus x2b squared plus x3a minus x3b squared plus dot 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 plus xna minus xnb squared, and then you're taking the square root of all those. So if, for example, we had a 3 dimensions like we had before, then this will be the first component from the first component of the second point, then the second component of the first point minus the second component of the second point B, plus a squared, plus the third component minus the third component of the B squared. So really, this is just a general formula, right, of the examples we actually gave here, where I took the first from the first squared it, the second from the second squared it, and the nth from the nth squared it, add them together and take a square root. Now, of course, this type of distance, right, that I define is not the only distance you can define, in a Euclidean space. There are other distance functions that you can define in Euclidean space. But not any function can be a distance function. The distance function needs to have certain properties. So not any function is a distance function. However, a distance function, distance A and B in Euclidean space, right? We can define it in many ways. In fact, any function raw between these coordinates of A and the coordinates of B that satisfies the following metric axioms is a valid distance. So for any distinct points, A and B, this function has to be positive. There is no negative distance, right? So the idea is that the distance between A and B is always positive, right? So if you can define a function raw, right, that is positive if A and B are distinct, so they're not the same point, then that's one property we need to have a valid metric. And now, of course, if B is A, then that should be 0, right? So the other thing is that for any point A, if you take the distance between that point and itself, right, then it should be 0. And also it should be symmetric because the distance from A and B should be the same as the distance from B and A, right? So if you're able to define a function, right, that satisfies these three axioms, the positivity if two points are distinct, the equality to 0 if this point is the same point that you're taking the distance to, and the symmetricity property, then you will also have a valid distance in that Euclidean space. So in other words, it's not only that you can define the distance as I told you, right, where you just take the component, subtracted, square it, add second component, subtracted, square it, and then take a square root, right? You can actually do more than that. And by defining this function rho, and that function rho, if it satisfies the metric axioms of having a valid distance, right, between, of being positive if the point A and B are not the same, or if the point A is the same point and you try to take the distance as 0 and they are symmetric, then thus you still have a valid distance. And the last part, what we need is we need to have this triangle inequality to hold. So if you have 3 points, A, B, and C, we would need that the distance between A and C to be less than the distance between A and B and the row or the distance in this example, B and C. So the idea is that we need the 4 points to hold, and then you would have a valid distance measure. So this triangle inequality is saying that if I give you 3 points, let's call them A, B, and C, the distance between, or the row in this example, between A and C should be less than the row between A and B plus the row between B and C, okay? So examples of this are numerous, but one of them is the Manhattan distance, which maybe you've heard of, right? But the Manhattan distance is defined as the sum of the absolute values between the components of the point A and the components of the point B. So I give you 2 points, right? And then those points, the way you can define a Manhattan distance, I think it's also called a taxicab distance, is that you can sum the absolute value differences of all those components. Now, this meets the metric axioms, and consequently, it's another form of distance we can define in a Euclidean space. Okay, So we talked about Euclidean spaces so far. We talked about what they are. We talked about that we need coordinates, right, to specify points in that Euclidean space. And now we also talked how you define distances. And now we're going to switch a bit and talk about vectors. So what is a vector? A vector, right, in a Euclidean space is a geometric object. So it's dictating the geometry, right? It's dictating the geometry. It's a geometric object. But that geometric object, right, it has a magnitude and it has a direction. So to define a vector, we need a magnitude of that vector and we also need a direction. Now, the vector itself is dictated or characterized by 2 points. So you will take the first point, right, point A, which has A1 up to AN coordinate values. So A1, what I used to call X, 1 of A, I just call it A1. So it's some value, right? It's like, let's say 2 on the first dimension, 3 on the second dimension, 4 on the third dimension, and so on to the n dimension. So it will have a beginning point A, like the vector will have the beginning point A, and it will have an end point B. So the vector will have a beginning point and an end point, where A, it is described, because it's in a Euclidean space, it's described by, if we are in Rn, right, by n coordinate values, and the point B as well by n coordinate values. So for example, the vector between these 2 points A and B, right? So you take the point A, which has, certain coordinate values in the x direction, y direction, z direction, and so on. And you would take the same for the vector B. And then you can define for the point B, sorry. And then you can define a vector between them, which starts at A, so that's the beginning point of that vector, and then ends at B. Now, please notice that the vector will have a magnitude, so it'll have a size, but also it'll have a direction. So here it's saying we're going from A to B, right? So there's a direction for that vector, because we could have defined a vector with a starting point or beginning point B and an end point A, right? Then the vector will be pointing in the opposite direction. So you can actually define a vector. For defining the vector, you would need 2 points. You would need a starting point and you would need an end point. And then from the starting point and the end point, you can, and each of those points, it has coordinates because we're in a Euclidean space, right? And then the vector will have a magnitude and a direction. So now the vector, right? The coordinates of this vector A to B, right? The coordinates of this vector from A to B is simply going to be defined as you would take the coordinate components on the end point and the coordinate components on the beginning point, and then you subtract them with respect to each other. So to describe that vector, we will have B1 minus A1. So you take the first from the first, you take the second from the second, and you take the n from the n, and you subtract them. So now that vector AB, I can write it as B1 minus A1, as B2 minus A2, as B3 minus A3, and as Bn minus An. So those are the coordinates or the components of that vector that goes from A to B. So now if I give you the data points, so I give you, 2 points. I give you a beginning point and an end point, right? So I give you a beginning point A and an end point B. And then I tell you, okay, what about this vector AB components? Then all you need to do is you'll take the first from the first, subtract them. That will be the first component of the vector. You take the second and subtract it from the second and subtract them. And please notice the direction. So I am taking the endpoint coordinate component from the beginning point coordinate component. And then I will do that across all the components of my vector. So then I will get the components or the coordinates of my vector AB. Right. So now to define the magnitude, right, of my vector AB, it's really typically defined by a distance measure between the points A and B. So as we said, the vector has a magnitude and it has a direction, right? So now, in order to be able to define the magnitude, what we first do is we define the vector coordinates or components by taking the endpoint coordinate component, subtracting it from the beginning point coordinate component, like we've done here, B1 minus A1, B2 minus A2, and so on. And then if I would like to get the magnitude of that vector, then it's the length of that vector, which is like a definition, which is used by a definition of a distance function. And now we know how to define distance, right, between A and B, right? So we take the first and the first component, square them, subtract them, square them, the second from the second, subtract them, square them, add those, and take a square root, like we've done before. So for example, here, right, if I have those points A, which is located in R2, and it has A is 1.5 on the X coordinate and B, and 1 on the Y coordinate. So to specify the point A, I need two variables, right? Because I'm in two-dimensional Euclidean space. So here, the A X coordinate is 1.5 and the B and the A Y coordinate is 1. And for the point B, which is another point I'm going to use to define my vector, right? I'm going to do 0.5 on the x-axis and 1.5 on the y-axis. So coordinate x is 0.5 and coordinate y is 1.5. Now, the vector that goes from A to B, right? The vector that goes from A to B, right? I'm going to take, how do I get its coordinates like we described here? So I'm going to take the first component, subtract from the first component. So I get 0.5 minus 1.5. That's like B1, A1, right? So I'm going to taking the first component of the point B and the first component of the point A, and then subtract them from each other. And then I'm going to do the same with the second component, right? And of course, I don't have n components. I just stop at the second component. And I'll take the second component where it will be the B2, which is 1.5, right? Minus the A2, which is 1. And then for the coordinates of this vector, or the components of it, will be -1 and 0.5. And now we just simply, if we want to understand the magnitude of that vector, we just simply take the distance between these 2 points. Now, let's look at a three-dimensional example, right? So Euclidean space R3. Imagine I have a point A. I want to define a vector, right, between a point A, which has 2.5, 2, and 1.5 coordinates, and a point B, which has 3, 1, 2 coordinates. So if we draw those, right, so this is my first coordinate X, my second coordinate Y, and my third coordinate axis Z. If I have A 2.5 to 1.5, then that means to localize this point A, I need to move 2.5 on the x-axis. So, and I need to move 2 on the y-axis, and I need to move 1.5 on the z-axis. And the same here, if I want to localize the point B, I need to move a 3 on the x-axis, 1 on the y-axis, and 2 on the z-axis. And now if I want to define the vector between A and B, that means I want to define a vector that goes from point A to point B. Remember, there's a direction, right? Direction is important. I'm going from A to B, not from B to A. Now the components of this vector, applying this formula here, will be, you will take the first component from the first component, so you will get 3. So that's the first component of the endpoint, 3, minus the first component of the beginning point, which is 2.5. So you will get 3 minus 2.5. And then you will take the second component, which is 1, minus the second component of your beginning point, which is 2. So you will get in this 1 minus 2. And then you would take the third component of the end point, which is 2, and the third component of your beginning point, which is 1.5. So you will get the vector that goes from A to B to have the components 3 minus 2.5, which is 0.5. Because remember, I've taken the first from the first. Then the second component will have the first of the end point from the first of the beginning point. So that's 1 minus 2, giving you minus 1. And the last is the 2 minus 1.5, which will also give you 0.5. Okay. Right. So so far, right, we have understood how we can, what is a vector, right? So the vector, needs 2 points. It needs a start point and it needs an end point, right? And then from the start point and the end point, you can define a vector. Its components, you will subtract the coordinates of the on, for example, the first from the end point minus the first from the beginning point. You will get the first component of that vector, then the second, then the third, and to the end, depending on how many dimensions your Euclidean space is in. Okay. Now, when we want to define vectors, right, we typically define them with respect to a reference point, right? And typically, the reference point for those vectors, so the beginning points of those vectors, is actually 0. So we're kind of seeing where that vector is with respect to the 0 point of my Euclidean space. So in this case, right, the point A will be given by zeros everywhere. So it will be like the point in the middle, 0, 0, 0. And now, therefore, right, if you actually talk about the vector AB, right, so going from A to B, going from 0 to B, it's really just the vector B. So it's just pointing it's an arrow pointing from the center of your Euclidean space to that point B. And if you do the subtraction like we've done before, right, we just will get the coordinates of that vector B. So you'll get B1, B2, up to Bn. Why you get B1, B2, up to Bn? Because remember, if you want to find AB, right, you will take the first component from the endpoint and the first component of the beginning point, and you subtract them. So you will have the first component of your endpoint is B1, right? And then you subtract that from a 0, so you get only B1. You take the second component, which is B2 here, and then you subtract from 0, so you get B2 and up to Bn. Now, we can also write this in an equivalent form by calling a transpose operator. So what we mean by that is that there are two notation we can use to describe vectors. One is we can keep it as a column vector. So we call it a column vector. It's a column vector. Or we can do it as a row vector. So we can either write it as a row or write it as a column. So these two are equal to each other via an operator, right, which is a transpose operation. So this transpose operation, you can think about it as it's allowing you to change the shape of that vector. So if you have a column vector, and you transpose that, then you will get a row vector. And if you have a row vector and then you transpose that, then you can get a column vector. Now, the notation we use for vectors is bold lowercase letters. So when I write a B lowercase in bold, that means I'm talking about a vector, a column vector typically of n dimensions, right? So that's kind of the notation you would see. So when you write B bold lowercase, then that's kind of a column vector with n components. So here are some examples. Here are some examples, right? So now, because we choose our center or our beginning point to be the point 0, 0, 0, or here in R3 to be 0, 0, 0, 3 zeros, right? Now, then the vector A, B, right, will be going from that point 0, 0 to that point B. So it'll have a point from a pointing direction from the 0, 0 to point B. And that would be this vector B, right? I could write this vector B here in terms of B1 and B2, right? So I can write the vector B as now it has a 0.5 minus 0, right, which is just 0.5, and 1.5 minus 0, which is just 1.5. So now I could write this vector B as 0.5, 1.5, right? And then I can use the bold notation, so small bold notation, in order to define that vector B. And now notice that this is a column vector, but I can equivalently write that as a row vector, but I would say I would like to transpose that row vector. That transpose operation would allow me to make the row a column or make the column a row. Now I can do similarly in 3 dimensions, right? So now my vector B would be the first component 3 minus the first component of my beginning point, which is 0 in our case, so 0. And then you would have 1 minus 0, and you would have 2 minus 0, right? And that will give you a vector of 3, 1, 2, which we can write in bold as 3, 1, 2, or we could also write it as a row vector, 3, 1, 2, not a column vector, but say, okay, I would like to transpose it. All right? So those are the some of the examples, right, of how you would, what we actually meant by this. Okay. Now, there are important operations you can actually perform on those vectors. So imagine I give you 2 vectors. Let's say I give you a vector V and I give you a vector U. Now that vector V, right, it has V1, V2 up to Vn, right? So it has n dimensional components, V1, V2 up to Vn. Again, like the point A or the reference point, beginning point is 0. And the vector U, which has like U1, U2 up to Un. Now what you could do is you can add those 2 vectors and you can multiply each by constants like alpha and beta. So we can do what we call a linear combination of those vectors. So what we can do is we can take the vector V, multiply that vector V by alpha, take that vector U, multiply that vector U by beta, and then we can add them together. So what we really do, or what we mean by that, is when you multiply alpha by the vector V, it means that you are multiplying every component in that vector by the value alpha. When you multiply beta by the vector U, it means that you're multiplying every component of that vector U by the value beta. And to add them together, you simply need to add the corresponding components of those vectors. So the idea here is when you multiply alpha by V, so you will get alpha V1, right, and beta U1, right, and then you just add them together. You get alpha V2 and beta V2, and then you add them together, and then you get alpha Vn and beta Un, and then you add them together. That's how you can form a linear combination of those vectors. So I multiply each component by constant. For V, it's alpha, and for U, it's beta, and then I just add them together. Now, of course, for this operation to work, both of those components need to have the same dimensionality. Okay. So what does this mean geometrically? What is happening geometrically? Like to just picture that. So if I have a vector u and a vector v, right? So if I have a vector u, which is like this vector u pointing in this direction, and this vector v pointing in that direction, when I do alpha v, right, if alpha is bigger than 1, so if alpha is bigger than 1, then I'm actually keeping the same direction of that vector v, but I'm actually scaling its components. So I'm making that vector v bigger, right? So because imagine, you multiply each of those components, right, in terms of a positive value bigger than 1, then you're actually scaling that. So let's take an example to actually understand this, right? So imagine, the vector v in 2-dimension, right, was made of, let's say, 2 and 3, right? So if I am looking into, this 2-dimensional plane, remember x, y, so it's our 2 Euclidean space. Let's say this is point 1, this is point 2, and 1, 2, 3, right? So now when I say I am 2, 3, right? So I mean I go on the x-axis 2, so boom, I'm here. And then I go on the y-axis 3, right? Right there. So that's my point. And then my vector, right, goes from 0 to that, so it's kind of pointing in that direction. Now, if you multiply by alpha v, where alpha is a positive, is bigger than 1, so let's say alpha was actually like 2 or something, right? Then how would we do alpha v? So alpha v would be 2 times 2, 4. So because as we said here, we're just going to take this alpha and multiply by v1. So I'll take the alpha multiplied by v1. And then here I get 6, right? Because it's 3 times 2. So now 2, let's say 3. If I plot this vector, right? 3, 4. And that's 3, let's say 4, 5, 6. Right. So now I will have a point that's somewhere there, right? So what I've done when I multiplied by 2, I actually kept the same direction, but I just increased that vector size, right? So that's exactly what's happening when we multiply, right, by alpha, where alpha is positive. So what happens really is that you take this value and then you actually just expand it, like keep the direction doesn't change, and then expand it. And now if we actually multiply the vector beta, the vector u by beta, but that's positive, right? But that's smaller than 1, then actually what we've done is we actually shrink that vector b. Because if we multiply by something bigger, if you remember the figure I just had, right? You would actually go, higher to 3, 6, I believe, right? We had in the example. But now, if you have a vector u and then you multiply its components by a beta which is less than 1, then we're actually shrinking that vector. And now, when we add these two vectors together, alpha v plus beta u, which is what we are getting here, then you will get this vector between them. So here's an example of this to better understand it. So imagine I have a vector v, which has, we are in 3-dimensional Euclidean space, right? I have 3 components. And now imagine I have a vector v, which has 1, 2, 5 components, meaning it has 1 in the x direction, 2 in the y, and 3 in the z. And I have a vector u, right? That vector u is actually 3, 9, 15, meaning in the x-axis it has a 3. I need to go 3, in the x-axis, 9 in the y-axis, and 15 in the z-axis. And now imagine my alpha is 2, so I'm doing 2v, and my beta is 0.5, so I'm doing 0.5 here. So first of all, I'm going to take 2 and multiply by every component in that vector v. So I will take 2 multiplied by 1, 2 multiplied by 2, 2 multiplied by 5. Okay? So then I will get 2 times 1, 2 times 2, 2 times 5. And then I'm going to add to that 0.5u. So 0.5u is going to be 0.5 times the 3, 0.5 times 9, and 0.5 times 15. And then I'm going to add those components. So you can form a linear combination on those vectors by, if you want to do alpha v plus beta u. And then the way you would do that is you will take alpha and multiply by every component in that vector v, beta by every component in that vector u, and then when you add the vectors, you just add the corresponding coordinates. Now, for this to work, as we said, we need to have the same dimensionality of the vector v and the vector u. So we need to be operating in the same dimensional Euclidean space. So here, to repeat, we take 2 multiplied by the vector v, right? So that's 2 times 1, 2 times 2, 2 times 5. We take 0.5 multiplied by the vector u, and then we add them together. Okay, so that's one operation we could do in a between two vectors. Another operation we can do between two vectors, which actually is a very important operation and becomes critical in machine learning, is what we call an inner product between the two vectors. So again here, okay, the vectors need to be of the same dimensionality. So u and v have to be of the same dimensionality. And the way we define the inner product is we will take those two vectors, we will multiply every component position together, and then we're going to add them all together. So the idea is, if I have a vector u and a vector v, so v1 up to vn, and a vector u, u1 up to un, when I do the inner product between the two vectors, I will use a notation that looks like this. So it's like a bracket, u, v, comma, v, another bracket. And it is really just v transpose u. So it means that, remember, what does v transpose mean? It will take the column vector v, and then it transform that into a row vector v. And then you will take the u, which is still a column vector, and then you will just multiply each of the components together. So you'll get v1, u1, v2, u2, add them, v3, u3, add them, plus, up to vn, un. Now, please notice that this result, if I do an inner product between two vectors, the result is not a vector, it's a scalar. So if you take the inner product between two vectors u and v, right, and you execute this formula, you notice that now the result is not at all a vector, but it's actually a real number. So the inner product between two vectors is just a real number. Okay. So the way we would construct this real number is we will take the first component from here and the first component from here, so u1, v1, then add that to the second component from here multiplied by the second component from here, v2, u2, and so on. So some properties of this inner product, first of all, this inner product is actually symmetric. So for example, if you do u transpose v or v transpose u, it's the same thing, right? So if I tell you take the inner product between v and u, right, it's the same as telling you take the inner product between u and v. If you multiply by zero vector, right, so if you do the inner product between any vector v or any vector u, right, with the zero vector, then you will get the scalar zero. Because if you think about it, if one of those vectors was made of zeros, so 0, 0, 0, 0, 0, 0, right, then what will happen is you will have 0 times u1 plus 0 times u2 plus 0 times u3 plus 0, la, 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 un 0 times un. So then you'll get 0. And now if you actually take the vector and you do the inner product with itself, what will happen? So imagine here I was doing v inner product v. So then here I will have v1 times v1, so that's v1 squared, right? Plus v2 times v2, that's v2 squared, up to vn plus vn, which will be times vn, which will be vn squared. So really, this, if you do the multiplication of the vector on itself, or if you do the inner product of the vector with itself, then you will get the sum of the components squared. Remember now that the square root of the sum of the components squared was the Euclidean distance, right? Now, if you take the inner product between the vector and itself, then it's just the sum of the components squared. So it is it's the distance we talked about, right? It's the distance we talked about without the square root, which we call the Euclidean length of the vector. And now, if two vectors are orthogonal, right? If we have orthogonal vectors, if they are orthogonal to each other, meaning they form like a 90 kind of degrees between each other, right? Then if you take the inner product between them, you will actually get 0. And then the linearity property holds. So if you have a vector, if you consider alpha v plus beta u transpose w, so notice that now I am doing the inner product, right, between this vector alpha v plus beta u. Remember how we compute alpha v plus beta u, right? Because we talked about it here, alpha v plus beta u. So if you have alpha v plus beta u, and then you do the inner product of that with the vector w, then this will be equal to alpha inner product of v by w plus beta inner product of u by w. So this is kind of a linear operation. So you will have alpha v transpose multiplied by w, which is the inner product between v and w multiplied by alpha scalar. And then you will have beta u transpose w, which is the u transpose w, which is the inner product between u and w multiplied by scalar beta. So here's an example. So imagine I have a vector v made of 1, 2, 5, and a vector u made of 3, -1, and 0.5. Now, if I do inner product between u and v, meaning that I will do u transpose v or v transpose u, remember, they're symmetrical, then what I'm going to do is I'm going to take the first component, 1 and the 3, right, and then multiply them together. So that's u1, v1, or v1, u1. Take the second component, multiply them together, so you'll get 2 times -1. Take the third component, 5 and 0.5, multiply them together, and then add them all together. Now, you've seen this. I think if you look at, for example, things in machine learning, you've seen this notation before, right? So this is, for example, in support vector machines, right? It is one example of using this notation, right? So, for example, in support vector machines, right, we can write this W transpose X minus V, which is equal to 0, which is like your maximum marginal hyperplane. But really, what this notation means, we're not going to discuss what support vector machines are, but the idea is that what this notation means is that you're taking the inner product between your weight vector, right, and your X input, okay? And the way you would take this inner product is just like this, you know? You would take the first component of your weight vector and multiply that by the first component of your X input. You add to that the second component of your weight vector, multiplied by the second component of your X input, etc., up to the n, depends how many weights you have. And now please notice, as we said, that W transpose X is a real number, right? Like it's a scalar, it's not a vector, because you just add those things together. So from those two vectors, W and X, if I did the inner product, I'll get a number. And now what I will do is I will subtract from it another parameter B, and that parameter B is also a number. So that's why this equation makes sense, because you can subtract a number from a number. All right. So far, concerning vectors, right, we have discussed a couple of operations. One of them is the linear operation of linear combinations, where we said alpha v plus beta u. And all you need to do is you multiply alpha by every component, beta by every component, and then you add the corresponding coordinates. We also discussed inner products, and then we said that inner products, all you need to do is you will take the first component and the first component, multiply them, add things together with the second multiplied by the second from the second vector, and so on. And this has nice properties like symmetricity. Like if you multiply with 0, you get 0. If you multiply with 0 vector, you would get 0. And if you multiply by itself, you get the Euclidean length of the vector. We have, if the vectors are orthogonal, you get 0. And it's also a linear operator. And then we took some example to do that. Now, there's another important operation which I think is used on vectors a lot in machine learning, which is what we call the component-wise product of the two vectors, right? So remember, this is not an inner product, this is a component-wise product. Typically, we signify that by this round, by this circle and a dot in between. When we write this circle and the dot in between, what we are actually meaning is that we have a vector u and a vector v, and then what we mean by this notation is a component-wise product between the two of them, right? So here, for example, if I have a vector v, v1, v2 up to vn, and a vector u, u1, u2 up to un, and then I write for you v circle dot u, which means that this is a component-wise product. It's as the name is, component-wise, you multiply the components together. So you get v1, u1 as the first component, v2, u2 as the second component, up to vn, un as the last component. Now notice that this result, because you do component-wise, you get as an output of this operation, a vector, right? You don't get an output of this operation, right, to be to be like, you don't take that to be a scalar like the inner product. This is a component-wise operation, right? Where have we seen this in machine learning? Well, if we actually look into things related to Adam optimizer, as I will show you later, you will actually notice that we are actually taking a component-wise operator. And here's an example, right, of this component-wise operator. All you need to do is you take the first component, 1 times 3, you get 3. Second component, 2 times -1, you get -2. A third component, 5 times 0.2, you get a 1. So yeah, so as I was saying, if you look into Adam, right, if you look into the update equations of Adam, you would notice that in the vector vt, for example, right, what we are doing is we're taking the gradient gt and we're doing a component-wise product with the gt itself, right? So we get gt squared, we get a vector of gt squared where every component in that vector is the multiplication of the components of the gradient, gt by gt, the first component squared, gt by gt, second component squared, and so on, right? So this notation, right, it really means that you just take the first vector you're interested in, which is in our case gt, in Adam, the gradient, and take the second vector you're interested in, which is gt in Adam, and then you can do a component-wise multiplication. So here you have a component-wise multiplication, as I said, right? So in Adam, like gt is your gradient vector. And that's a vector where you have the gradient across the first, weight and the second weights and so on, up to how many weights you have. And now when you do gt, right, gt dot round gt, then what we are really doing is applying this formula here. So we take gt, the first component, and the first component from the second vector, which is gt itself. So you'll get here gt1, and that's a squared, right? The first component squared, the second component squared, and so on. And also you can have a element-wise division, right? So in Adam, we also do an element-wise division. So for example, here we have this vector mt, which is, a vector, and we had vt, right, which is another vector. Remember, in that vt, we needed to do a component-wise product. And then in theta, right, we will have to divide, mt by the square root of vt plus epsilon 1. So those are the Adam equations. If you've ever, seen Adam, those are the Adam equations. So here what we are doing is we're also doing a component-wise division, meaning that you will take the first component, right, from the vector mt, divide that by the first component of the resulting vector of square root vt plus epsilon 1. And again, here square root is everything is happening component-wise. So square root is also happening component-wise. So in terms of notation, that's how we can write it. And now there is another thing we could do. So let's recap a bit, right? So what we've done so far is we talked about the vectors, and we talked that those vectors can allow you to do linear operations. So all you need to do is multiply alpha by every component and sum to that beta by every component of the other vector and add the components together. We also talked that you could do inner products, meaning that if you take one vector and another vector, right, and you multiply, you do the inner product by of these two vectors, that means you will take the first component by the first component plus the second component, plus third by third plus n by n, and we get a scalar, we get a real number. We don't get a vector if we do an inner product. But we also said that if you do a component-wise product, then you get a vector, right? So component-wise product was simply you take the first component and the first component of the second vector, and you multiply them by each other. You'll take the second, multiply them by each other, and then you'll take the third and the third, multiply them by each other, and then you will get a vector. Now, we saw that an application of this is an add-on. But now we can also take something called a Kronecker product between the two vectors, right? So everything we have described so far, they actually needed to have the same dimensionality, right? So they actually needed to have the same dimensionality of the vector u and the vector v. But now there's another product defined, right? And that product is called a Kronecker product. So for the Kronecker product, the two vectors can have different dimensionality. So here we can take the vector v, v1 up to vn, and the vector u, u1 up to um, and they can have different dimensionality, m and n. So how many components, right? I'm working in n for vector v, and I'm working in m for vector u. Now those components could have a different, right? A different dimensionality. So n does not have to be equal to m. It can be, but does not have to be. It's defined more generally. Now, the Kronecker product between these two vectors, right, is defined as v1 times the whole vector u. Notice, I take the first component, right, of v1, of the first vector, so that's the v1, and I multiply that by the whole vector u. So I take u1, u2, up to um. So this u bold, remember our notation, bold u small is a vector. Cool. So now what we do is we take the v as a Kronecker product with u, and then what we are going to do is the first part is going to be we take the first component and multiply that by the vector u, by the whole vector u. And remember, we know how to multiply a scalar by a vector. So this is like alpha times u, where alpha is v1 in this example, right? So you just need to multiply every component of that vector u by the v1. v2 times u is the second part. So you'll take the second one again by the whole vector u. And you do that up to vn multiplied by the vector u. So the Kronecker product between two vectors, the first part of it will be the first component from the vector v multiplied by the whole vector u. The second component from the vector v multiplied by the whole vector u, the third component multiplied by the whole vector u, up to the nth component multiplied by the whole vector u. Now, how do we multiply, those vectors together? Well, in order to multiply those together, we just need to multiply an alpha, or v1 in this example, by the whole vector u. So that means that we just need to multiply this v1 by every component in that vector u. So you will get v1 u1, v1 u2, up to v1 um, right? So this chunk is just dealing with the u1 times the whole vector v. Then you will have another one which is v2 times u, so you will get v2 u1, v2 u2 up to v2 um. And then you will have the last one which is vn by u, so you'll get vn u1, vn u2 up to vn um. Okay, So if you had a vector in Rn, which was your V, Rn Euclidean space, we know what that means. If we had a vector in U in Rm Euclidean space, we know what that means. Now notice that the size of this vector, right, will be Rm times m. Why? Well, okay, the first thing we have is we have the V1, right, multiplied by the whole vector U. So that will give me m components. So that's the first m components right there, m components. Then you take V2 multiplied by U again, right? And that's the second m components, right? Then you will have here V3 by U again, which will give you another m components. And then you're doing that n times. So you'll get a vector of size Rn multiplied by m. Now, here's an example. Notice that we have V1, 2, and U, which is the 3, minus 5, and 20. Notice that the U here is 2 dimensions, and the V is 3 dimensions. So n and m are not the same dimension. N is a 2 dimensions, so n equal 2, and m equal 3. So what we're actually doing is we're taking the first component, so we're doing V1U first, so we're taking the first component of V multiplied by the vector U, so you will get 1 times the 3, then you will get 1 times minus 0.5, then you will get 1 times 20, right? So that's the first one, V1 times U. I'm taking the first one and multiply by the whole vector U. Then I take 2, because now I need V2U. So I take 2, multiply by the whole vector again. So I get 2 times the 3, then I will get 2 times minus 0.5, then I will get 2 times 20. All right? So that's how we compute this Kronecker product. Okay, so now we have, if we remember, we talked about three or four things, I think. So first we had this linear combination of vectors that taught us how do you multiply a scalar by the vector plus a scalar by the other vector, and you can add them together. Then we talked about inner products, where you take the first component, multiply, add to that second component, multiply, add to that n component, multiply. And then we said that that gives us a real number, right? So that does not give us a vector, remember? So let's go back and just recap this a bit, right? So here, a inner product will not give us a vector, it'll give us a scalar. However, a componentwise product dignified by this round dot thing will give me a vector. And the way that componentwise product works is just by multiplying the first component by the first, the second by the second, and so forth. And we saw that that could happen in Adam, for example. Okay. And then we talk about the Kronecker product. Now, the Kronecker product, critically, the dimensions of the vector don't have to align. They could be different things. You will take the first component of the first vector, multiply by the whole second vector. Then you would have the second component of the first vector, multiply by the whole second vector, and so on up to the nth component. So as we show here, first by the whole vector, V1U, second by the whole vector. So therefore, if you had n and m, then you will have a resulting Kronecker product of n times n, and then we did an example. All right, cool. Now we talk a bit about vectors and vector norms. So we've been talking about vectors, sorry. And now what we could do is we can define a norm of a vector. And that norm notation typically has, you know, these 2 lines dot and 2 lines between them. So 2 lines vector v, 2 lines between them. Now that is a vector norm. Now the norm of a vector is any univariate function that satisfies the following norm axioms. The first axiom is the definitiveness. So if the norm of the vector is 0, then that means the vector itself is 0, right? So if we had the norm of the vector to be 0, then that means that the vector itself has been 0. Then we have something called absolute homogeneity, meaning that if you actually consider the norm of the alpha times v, right? So a constant times v, that is the same as taking the absolute value of that constant alpha and take the norm of that v for any vector v and any scalar alpha. And we also have the triangle inequality holding. So the norm of the sum is less than the sum of the norms. The norm of u plus v is less than the norm of u plus the norm of v for any two vectors u and v. And of course, non-negativity, meaning that the norm of the vector v has to be greater than 0 for any vector v. Of course, it can be equal to 0, so greater than or equal to 0. So a norm has this notation, and it satisfies the norm axioms. Those norm axioms are: if the norm is 0, then that means the vector has been 0. If we multiply vector alpha, multiply scalar alpha by v and take the norm, that is like taking the absolute value of alpha multiplied by v. If we the triangle inequality holds, so the norm of u plus v is less than the norm of u plus the norm of v, and we have non-negativity, meaning that the norm is greater than or equal to 0. So where do you see some notation like this in machine learning? Well, if you are training, right, a machine learning model, sometimes you decide to add a regularizer, right, to your machine learning loss. So you would minimize with respect to the weights, right, the standard loss with respect to the weights and the data, and then the data. Like, for example, this could be MSE, right? And now you add a regularization term to avoid overfitting, for example, right? So in order to avoid overfitting, you might kind of add this regularization term. And this regularization term is actually, maybe you can see, would have seen this notation, which is the norm of W, and that's a regularization term. So when we are looking into the norm of W, we're talking about one of those univariate functions. Now, so there are different types of norms, right? We can define on vectors. So, for example, we call it the L2 norm, the L2 norm, and that is because we will use this notation. So we will have this bar, the vector v, this bar, and then put 2 there, right? And that would be the L2 norm, we call it. And that L2 norm is just the Euclidean distance, right? We talked about before, which will mean you will take the first component, square it, the second component, square it, up to the n component, square it, and then you take square root from those. So that is what we call the Euclidean norm. For example, right here, if I give you a vector v, which is 1, 3, and 5, remember, I just used transpose here, right? So what I really mean is that this is a column vector, right? Because I could flip it because I'm using the transpose notation. And now I look at the norm of that vector v, then I will just do the square root of 1 squared plus 3 squared plus 5 squared. Because I will take the first component, square it, I'll take the second component, square it, I'll take the third component, square it, and add them together. So I just use this definition, right? So first component square plus second component square up to the nth component square. And then, you would add them together, so you will get this form of a Euclidean norm. And now please notice, as we showed before, actually, the Euclidean norm satisfies, these norm axioms, which is described before, right? So these, that we have definitiveness, absolute homogeneity, sub-additivity or triangle inequality, and non-negativity. Okay. We can also define another form of a norm, which is called the L1 norm. That L1 norm is just simply defined as the notation is bar, bar, vector v, bar, bar, and then 1, just to say it's an L1 norm. This was L2 norm or Euclidean norm. And that would be just the sum of the absolute value of the components. So for example, if you had a vector u, which is 1, minus 3, 4 transpose, then if you take the L1 norm, it will be the absolute value of 1 plus the absolute value of minus 3 plus the absolute value of 4. So absolute value of 1 is 1, absolute value of minus 3 is 3, because that's the absolute value operator, and the absolute value of 4 is 4, then you get 8. You can also define something called infinity norm. So we use the following notation: bar, bar, vector v, bar, bar, and subscript infinity. And the infinity norm is defined as the max over all the absolute value of the components of the vector v. So So for example, if we had a vector, let's say, of -20, -3, and 8 transpose, right? Then the max norm of that vector W will be the max of the absolute value of -20, of the absolute value between the absolute value of -20, between the absolute value of -3, and between the absolute value of 8. And now absolute value of -20 is 20, absolute value of -3 is 3, and absolute value of 8 is 8, then the max of this is 20. So the L infinity norm, or the infinity norm of this vector W, right, is 20. Okay. And we can also define another norm, which is what we refer to as a sparsity norm, right? And now that sparsity norm, right, is what we call L0 norm. So the notation is you would take the this bar, bar, V, bar, bar, and subscript 0. And that is defined, right, this sparsity norm L0 as the I in the dimension of that vector, so 1 to n, such that the component Vi is not equal to 0. So what you're actually counting is you're counting how many non-zero elements the vector has, right? Because every time you would get you would get a non-zero value, you will save the index, and then you're taking kind of the cardinality of that set. So you will see how many non-zero elements you have in that vector. So for example, if I look at H vector of 0, -3, 0, and 4, right? Then if I look at the I where I have non-zero elements, it will be this component and that component, and then I will take the cardinality of that set, which is 2. Okay. Right. Now, all those are norms, right? However, one of them is not actually a norm, and which one and why? I'll give you the answer, and that is the sparsity norm. But what I would like to do is I would like to ask you to think about this. Why do you think the sparsity norm is not the valid norm? And actually, maybe you can write your answer in the comments below this video, and we can have a discussion if it's not clear. Okay? Now there are relations between norms of the vectors. So for the same vector V, we could define different types of norms, right? Because as you saw here, right, for that vector V, I can define an L2 norm, I can define an L1 norm, I can define an L infinity norm, I can define an L0 norm, and maybe other norms. So now there's an equivalence relationship between these norms. So if I have two norms, the P norm and the Q norm, so remember, what do I mean by P and the Q, right? I mean by P and the Q is that, P here is 2, for example, P here is 1, P here is infinity, P here is 0, right? And if I am interested in the norm of a vector VQ, then we can actually have an equivalence relation between this norm in Q and the other norms in V. And this allows us to have the equivalence of these norms. Now I will give you an exercise. So what I would like you to prove for us is that imagine you have this is some valid norm, right? And then you would have that this U and V norm is a valid distance function between the points U and V, right? So the question is, right, imagine that you have this notation, bar, bar, dot, bar, bar is a valid norm. Then the norm between U and V is a valid distance function between the points U and V. So that's one thing to try to prove. Like, why is this a valid distance function? And then for any two vectors, remember the scalar product we had, right? So remember we had the scalar product before, that the absolute value of the scalar product is less than the norm of U and the norm of V. So this is an exercise that you can think about. And maybe write in the comments below if you have any questions and if it's not clear to actually solve this problem. Okay. With that, I would like to end the first part of this lecture. I hope it was not too boring, but we will continue next with more stuff related to vectors, and also we'll jump into matrices. which will allow us to the necessary jump to neural network, especially in the forward pass. So with that, I will end the first part, and then I will see you in the second part. So thanks a lot.